Okay, welcome to Chapter 12, Section 3 on Newton's third law. So let's get right into what the key ideas here are, our key questions. So what happens when an object exerts a force on another object? How do you calculate the momentum of an object? And what is the total momentum after objects collide? Let's move through the bell ringer here. So let's talk about action and reaction forces. So what happens when an object exerts a force on another object? When one object exerts a force on a second object, the second object exerts a force equal in size and opposite in direction of the first object. This is called Newton's third law. You may have heard it simply as every action has an equal and opposite reaction. But we say it a little more technically here is when one object exerts a force on a second object exerts a force equal in size and opposite in direction on the first object. And it's key to remember there that it is equal in size and opposite in direction. Alright, so forces always occur in pairs. Just like we said a second ago, for every action force there's an equal and opposite reaction force. That's where action-reaction pairs come in. So forces in a force pair do not act on the same object. Equal forces don't always have equal effects. For example, the action force of the earth pulling on an object and causing it to fall is much more obvious than the equal and opposite reaction force of the falling object pulling on the earth. So when you go and jump off the high diving board at the pool, the earth is pulling you toward itself, but being a mass you are also exerting a force on the earth. Since the earth is way more massive than what we are, we don't see the earth move toward us. We have a larger acceleration. The earth has a very small acceleration. Alright, so action-reaction forces. Let's watch and listen to the video.
Newton's third law states that if two objects interact, the magnitude of the force exerted on object 1 by object 2 is equal to the magnitude of the force simultaneously exerted on object 2 by object 1, and that these forces are opposite in direction. A simple way to remember Newton's third law is to remember that forces always exist in pairs. That is, for every action, there is an equal and opposite reaction. The hammer exerts force on the nail. The nail resists the force.
Okay, so as the hammer hits the nail, it exerts a force on the nail, but the nail also exerts an equal force, remember that as far as action-reaction pairs, an equal amount of force on the hammer in the backward direction, which is how the hammer comes to a stop. Moving on. Momentum. How do you calculate the momentum of an object? So, for movement along a straight line, momentum is calculated by multiplying an object's mass and its velocity. And part of the thing with momentum here is momentum is easier to study when we're talking about collision of objects and objects interacting in collisions. It's easier to talk about momentum before a collision and momentum after a collision, or just calculate the momentum of a moving object, instead of trying to deal with the forces, because those can kind of vary as the objects go through the collision. So momentum is mass times velocity, or momentum is represented with the letter P is equal to mass times velocity, or m times v. So momentum is a quantity defined as the product of the mass and velocity of an object. So the definition of momentum here is just the equation of what momentum is, product of mass and velocity, multiply mass times velocity. I'm just saying with momentum we use it to study collisions more, because we can measure the mass and velocity of an object before it collides, and we can measure the mass and velocity of an object after it collides, and then we can study those and find out what happened in a collision, instead of trying to study forces during a collision. That's very difficult. So mass and velocity of an object. The SI units of momentum is kilograms times meter per second, so a kg times m/s. Momentum and velocity are generally, have to be, actually always, have to be in the same direction. So if an object has a velocity and a mass, so the mass times that velocity, the momentum is always in the same direction as that velocity. Momentum increases as mass increases, or velocity increases, or both. So the larger the mass, more momentum. The larger the velocity, more momentum. If you increase both, you increase momentum as well. Force is related to the change in momentum. So as for the period of time the momentum's change becomes longer, the force needed to cause that change in momentum becomes stronger. That's called impulse momentum theory, in that a force causes a momentum change, and we've studied about that. Force is equal to mass times acceleration. So it can change an object's motion. The force needed, as the time increases, you can have a smaller force applied over a longer time will change the object's momentum just as much as a large force over a short period of time. Alright, so talking about momentum here. Calculate the momentum of a 6 kilogram bowling ball moving at 10 meters per second down the alley toward the pins. So let's again, givens and unknowns. We have given that the mass of the bowling ball is 6 kilograms. Velocity is 10 meters per second, and that's going toward the pins. Direction's important there. So unknown, it says to calculate the momentum. So that's what we don't know and what we need to calculate. Again, write the equation: momentum, mass times velocity, or P is equal to m times v. And then we just insert the values: 6.0 kilograms for mass and 10.0 meters per second for the velocity. We multiply those two, and you get 60.0 kilograms meters per second, and the direction is toward the pin. So that's how much momentum the object has. Now let's talk about the conservation of momentum. So what's the total momentum after the objects collide? And remember, I talked about we can study momentum of an object before the collision and after collision. So this is talking about after the collision now. So the total momentum of two or more objects after a collision is the same as it was before the collision. So in other words, total amount of momentum in an isolated system is conserved, which means the momentum of those objects that you're considering are the same before they collided as after they collided. So it gives you a good way to kind of see what goes on and how energy is transferred. This is basically called the law of conservation of momentum. So this little video is going to give us a demonstration of that.
The concept of momentum is particularly useful in determining the results of collisions between objects. The law of conservation of momentum states that the sum of the momenta of objects after a collision equals the sum of the momenta of the objects before the collision. In other words, momentum is conserved in collisions. In the two cases shown here, the masses of the objects are equal.
Okay, so this one had a kind of a big long well, it won't pause for me, but then you saw that big long equation. In this case, you have two balls that are of equal size. One has motion, one does not, but they are of equal mass. Together, in the beginning, the red one's not moving and the blue one is. So the blue one is the only one that has momentum. So you take the momentum of it plus momentum of the red ball, which is 0. So you have just that momentum. After the collision, the red ball's moving and the blue one stops. So basically it's transferred all of its momentum to the red ball, and now the red ball has the same velocity as what the blue ball did originally. That's if they are exactly the same size or same mass. If they are not the same mass, then that would not be the case. If the blue ball had a larger mass than the red one, it would give a fairly large velocity to the red ball, but it would still keep moving at a slower rate. If the red ball was more massive than the blue one, the blue would actually probably bounce back in the other direction, and the red ball would move forward with some slower velocity than what